Hi, math students. My name is Patti Frazer Lock. I'm a professor of mathematics and statistics at St. Lawrence University, and we're going to be talking today about math and urban planning. So let's go there. Here we go, math and urban planning. These dots and lines at the bottom of the screen here are called graphs, and they're part of an area of mathematics called graph theory or network theory, which is my research area. So let's get started with a historical problem, the Königsberg Bridge problem. So Königsberg is a city in Russia, and it's, I think, now called Kaliningrad, but it looks like this. There's a river running through it. It's called the Pragal River. And so here's the river coming in here. It splits around this island and then it splits again over here. And there are 7 bridges. So here's the river. These are the bridges. There's one, and so on. All right. And the citizens of Königsberg in the mid 1700s were trying to solve a puzzle. They were trying to figure out if they could walk around the city, starting anywhere, cross every bridge exactly once, and return to the start. So suppose they started up here on this side of the river. They aren't allowed to swim across the river to get to a new place. So if they're over here, they might walk around, they might cross this bridge, and then maybe this bridge, and then this one, then they might walk way over here and cross this one and keep trying to do it, all right? That's the challenge. And that's your challenge, because trying to see if this is possible to cross every bridge exactly once and return to the start is the second problem on the worksheet that you're going to do momentarily. All right, welcome back to that. The first problem is about delivering the mail, urban planning again. So this is a very small town, all right? It only has these 1, 2, 3, 4, 5, 6, 7, 8 roads and intersections. And the goal is this: the mail carrier wants to deliver the mail efficiently. She needs to walk down every street because she's putting the mail in the mailboxes, but she would really ideally like to walk down every street exactly once, no repeating any streets. And she wants to start and end at the post office, which is the thing labeled X here. So she has to start and end at X. She has to go down every one of these edges. So you can think about maybe how to do that. And she has to get back to X. So cover every street to deliver the mail. Don't repeat any of them and get back to the X again. So I'll let you think about that for a minute. Can she do it? Yes or no? So here's what she might do. There's multiple answers here, but she might start out going that way with the red arrow. And then she has a choice to make. There's 3 different ways she could go. Maybe she goes out that way, and then she goes back. Of course, no choice there. She has to pick up these 3 at some point, because if she goes here now, she'll get back to the post office too soon, and she'll miss some streets. But it's easy enough. She could go there, she could go there, she could go there, and then head back to the post office on those 2. We just did it, okay? We covered every single street. We didn't repeat any, and we started and ended at the X. That's the goal. So the answer is yes, she can do it, and we just showed how. We just showed one way to do it. There's other ways too that work. Here's a second example of the same thing, an even smaller town now. Same rules, walk down every street exactly once, and begin and end at the X. So I'll let you look at it and think about it for a minute. Can she do it? Yes or no? So if she started out this way and gets down to here, she could go back, but then she's missing 2 streets. She could go here, but then she's missing that middle street. And you can try other ways of starting and other ways of continuing on. But no matter how you try, it's impossible. So she cannot go down every street exactly once in this town and begin and end at the X. Okay, that's your challenge. I'm going to give you a whole bunch more graphs or maps like this. And in every case, the rule is this: walk down every street exactly once and begin and end at the X and say yes or no, just whether you can do it or you can't do it. So pause the video now and do worksheet 1. And there's 2 pages. Restart the video when you're ready for the answers and I will wait. Okay, welcome back. Hopefully you paused the video and had a chance to look at the worksheets. Let's look at the problem 1 on the worksheet. First, the delivering the mail. So here's what you may have found. Here are the correct answers. For A, the answer is yes, you can do it. For B, it's no. For C, it's yes. For D, it's no. For E, it's yes. For F, it's no. For G, it's yes. For H, it's no. And for I, it's no. So you can raise your hand if you got them all right or something. Let's look into this more deeply. So here's one where the answer was yes. Here's one where the answer was no, and they're not really all that different looking. So the question is, why is one of them yes and one of them no? What is the critical difference? Were you able to think about this as you were working on worksheet 1? So you may have noticed that every time you go, say we start at X, every time you go into a vertex, a dot, and out again, you use 2 edges. If we then go back into that dot and out again, we also use 2 edges. Every time we go into a dot and out again, we have to use different edges every time. We use 2. So it would appear that the number of edges coming into a dot has to be even. And in fact, that is the rule. If we look at this one where the answer was no, I just circled that one because that has 3 edges coming into it. So you might use 2 of them, but then when you go back in, you're stuck there, right? You can't get out again because there's not an exit road. Likewise, that dot right there has 3 edges coming into it. Those are odd. And in fact, intersections with an odd number of streets mean the answer has to be no. And in fact, this is the huge theorem that Leonard Euler proved in 1736. It's called Euler's theorem. It's spelled like that, but it's pronounced Euler. And the theorem says this: it is possible to walk around a street map and cover every street exactly once and return to the start, if and only if every intersection has an even number of streets meeting there. It's a completely determining condition. And we can check it with these, right? With this one, this has 2 streets, this has 4, this has 2, 2, 2, 4, 2, all even, and the answer is yes. Over here, this has 3 streets meeting there. The answer is no. This you can check. We already went through this one. This one has all even, and it's yes. This one has an odd there and there. It's a no. This one has all even. It's a yes, and so on. You can check all of them. It's a very, very quick thing to check to get a yes or no answer on this walking down every street exactly once problem. So let's go back to the Königsberg Bridge problem, because this is the question that led Leonard Euler to prove his theorem in 1736. So again, the Königsberg Bridge problem asks, is it possible to start anywhere, move around the city and cross every bridge exactly once and return to the start? That's what they were trying to do. And Leonard Euler actually visited Königsberg in person in 1736, and it was trying to answer this question that led him to the big theorem on the previous slide. And Leonard Euler is the most prolific mathematician that ever lived. If you go on and take more math classes, you'll hear his name again. His work appears in virtually every area of mathematics, including, Algebra 1, and it's all over the place. He did a huge amount of work. Okay, so what did he do with the Königsberg Bridge problem? He decided this. He said, we're going to draw a street map where the land masses are dots, because if you're over here on this side of the river, you can get to any one of these three. It's just like a single dot. And the bridges are the edges, because those are the things we're trying to cross once and only once. So let's make the dots. Here's a dot for the top side of the river up here. Here is a dot for the island that's labeled A. Over here is a dot for this landmass D, and here's the bottom side of the river. So only four dots. Let's put this bridge on, all right? It goes from the top of the river to this landmass D. It's an edge right there. Let's put this bridge on. It goes from this landmass over to A. We'll put this bridge on. It goes here. Over here, this is Island A, this is the top side of the river, and there's two bridges there. So we're going to draw two edges, that one and that one. Likewise, two bridges down here, we're going to draw two down here. And if you check how many of the edges end at each of these dots, this one has 3, this one has 5, this one has 3, this one has 3, or you could be counting bridges over here. But they're all odd. There are odd intersections. Euler's big theorem showed that if there's odds, the answer is no, and this is impossible. So I hope you didn't spend too much time on it, because it is, in fact, impossible to start anywhere, cross every bridge exactly once, and return to the start. Okay, so Euler's theorem is great. It tells us a really fast way to look at a map and see if we can do every street exactly once. Question is, does it have value? And the answer is it has an absurd amount of value. You do have to modify it, because usually we have to walk down every street. We don't care if we repeat some, but we want to do it as efficiently as possible. And you can extend Euler's even odd idea to see how to do that in the most efficient way. And in fact, this idea of using even odd intersections has saved the cities that have used it millions of dollars. It's quite remarkable. So when you think about who might want to walk down every street in the most efficient way possible, or drive down every street in the most efficient way possible, you've got mail carriers and snowplows and garbage trucks and street cleaners and meter readers and police patrol and maybe vacuum cleaner salespeople or others that I haven't thought of. There's a lot of different reasons you might have to walk down or drive down every street in a town. And if we can find ways to do that more efficiently, like trash pickup, for example, or street cleaners, it saves an absurd amount of money. So it has a lot of value, and yet most towns and cities don't know this mathematical solution yet. I'd say maybe 10% of them are using it and saving all that money. But most of them, they're not mathematicians, these urban planners. So you could sign on as a consultant right now with almost any city or town and save them lots of money using just this idea of even and odd. Okay, that is the first topic. We're going to do a quick second topic, and it is for the mail pickup people. So what about the mail pickup people? So we help the mail carriers who have to go down every street as they deliver the mail. The mail pickup people are just gathering the mail from the drop boxes at every intersection. They don't have to go down every street. They just have to go through every intersection. So now the question is there a way to begin and end at the post office? So we're still starting and ending at X, and pass through every intersection or every dot exactly once. So here's an example. So I'll give you a minute to think about this. Can you start at X? Can you move around the graph in a reasonable way as if you were driving on the streets or walking on the streets, and pass through every dot, not every edge, every dot, exactly once? I'll let you think about that. So the answer is yes. And there's one way to do it. So you could go in any direction here. Suppose we start on X, we go this, we go here, we go down and pick up that dot because we have to go through every dot, and we go back. Notice we don't care about the streets, we just have to go through every dot. So it's a different question than the last one. This is for the male pickup people. So that's the question. Can you begin and end at X, go through every dot exactly once, and get back to the start? This example is yes. Some of the ones on your worksheet will be yes, some will be no. And so that is the next thing. So pause the video again, do worksheet number 2 now on the male pickup problem, and restart the video when you're ready for the answers, and I will wait. Okay, welcome back. Hopefully you paused the video and looked at worksheet 2. Here are the graphs that were on worksheet 2, or the street maps, if you like. I will draw the answers on these ones. So the first one is yes, and there's one way to do it. I guess that's the only way to do it, is to just go around the outside. Notice you're getting every one of the dots. It's good. And you're starting and ending at X. For the second one, it's also yes. And again, you can do it just by going around the outside in either counterclockwise or clockwise. For the next one, you can't. You can try and try, but you can't do it. For the next one, you have to jump in and catch those ones in the inside, but you can do it. And here's probably the only way to do it also. Again, you can go in either direction. For E, you can try, but you can't do it. For F, you can try, but you can't do it. For G, you can try, but you can't do it. You would have to repeat this one, and you're not allowed to repeat a dot. For H, you can. There's a variety of ways you can do it. The answer is yes. Here's one of the possible ways. And for I, the answer is also yes. So again, raise your hand. There's one way, there's multiple ways. Raise your hand if you got all the yeses and nos correctly. Notice the E and I are kind of the same kind of grid graph, but one's yes and one's no. And again, the question is, what is the distinguishing thing, right? What is there about these graphs that makes some of them possible, some of them not possible? Maybe you thought about that as you were figuring out the yeses and nos. Did you come up with a quick way, like the even odd idea, to tell whether it's a yes or a no? Well, if you did, you will win a Nobel Prize and immediately get a PhD in mathematics from Harvard University or something like that, because you would be the first person to figure this out, because nobody knows. Many mathematicians and computer scientists have worked on this over the decades and, in fact, centuries, and no one has found a way to do it. And in fact, it's one of the most famous open questions in all of mathematics. These are called Hamilton cycles, and it's called the Hamilton cycle question. Okay, this is network theory. And sometimes we have great answers, like our even odd Euler's theorem gave us really good answers that really help with a lot of practical problems. But sometimes we don't know the answer yet, and we may never know the answer in some cases. This is called network theory or graph theory. It's important in urban planning. I've shown you a little bit of that, but it's also used to study social networks like Facebook and Instagram and Snapchat and all of those, and also things like in human networks and terrorist networks. The NSA and the CIA study terrorist networks using a lot of this network theory stuff. But it's also important in neural networks in the brain, so it's important in neuroscience. It's also important thinking of how species interact in an ecosystem, and on and on. And it's dots and lines, and so it's also very common in puzzles, for example, and lots more. Anytime you have individual things interacting, that's network theory. Thanks for joining me for this quick introduction to network theory. I hope you enjoyed working on the workshops. I will stop sharing, say goodbye, and enjoy the rest of your day.